Hi, this is Barrett Givens from Cal Poly Pomona, and this video is for my Math 419 students. This video is from section 1.6 in the textbook. The topic of this video is the replacement theorem. So the replacement theorem is sort of the fundamental theorem of this section. All of the really important facts about basis and dimension come from this theorem. So I want to make this video to kind of help you understand what the theorem is saying and also help you understand the proof in the textbook. Okay, so in the theorem we have this set G, which is big, and it spans V. So I'm going to write G as W's like that. And then I have a set L, which is little and is linearly independent. So L is V1 to Vm. The idea is that L is linearly independent, but L might not span the whole set. L might be too small to span the whole set. Imagine like L could be just like one vector in R3. Okay, that would be linearly independent. And so what we want to do is we want to take some elements of G, just like some random elements, who knows which, and we're going to put them into L. And we'll call those elements H. Whichever ones we choose from G to go in there, we'll call those H. And the big punchline of the theorem is that if you choose them correctly, then L union H, which will be the things in L plus some of the things from G, will span the whole vector space, okay? And then finally, the other fact is that the number of elements in L union H should be the same as the number of elements in G. So another way to think about it, instead of thinking of taking particular elements of G, like the ones I've circled, and putting them into L, I could think about it the other way. I could think about taking the elements, the V's, V1 to Vm, and taking each one and replacing some of the elements in G by some of the elements of L. So I'm replacing a few of them. So that's why it's called the replacement theorem. So I can either think of adding stuff from G to L, or I can think of replacing stuff in G by stuff in L. Okay, before we start, there's two facts that are going to be really useful in this theorem. The first fact is that if L is linearly independent and V is an element of L, then V cannot be written as V is not an element of the span of the things in L other than V. Okay, if V could be written in terms of the other elements of L, then L would be dependent. The second fact is, if I take a set that I know spans V, and then I remove an element W and add an element V, if my W can be written in terms of G' and V, then G' and V spans the whole vector space V. So the idea of this second fact is that if I have something that spans V and I remove one element, the purple one, and I add a blue one, then this condition right here, this is the condition that I have to know that by removing and then replacing, I still span the whole set. Okay, so think about those two facts, maybe pause for a minute and think about how you would prove them if you needed to prove them. They're both things you should be able to prove at this point. And then we'll move on to the proof. Okay, so now let's talk about the strategy for the proof. We're going to consider one element of L at a time, and what we're going to do is we're going to choose a single element W from G that's going to be replaced by this element of L. I'm going to call this element V, which means I need to have said what V was at the beginning, so I'll put that up here, V. We'll consider one element V of L at a time, cleverly choosing a W from G, which can be replaced by V. So we can't just do it at random, we have to think about how we choose that W. Okay, well we'll start with V1. Why not? We'll just pick V1. G spans the whole set, so I can write V1 as a linear combination of elements of G. So there's V1 written as a linear combination of elements of G. Now, could all of those constants be zero? Could all of those constants be zero? Well, if they were all zero, then V1 would be zero. But L is linearly independent, so V1 can't be zero, which means those constants can't all be zero. So at least one of them has to be non-zero. Now, it could be C1 is not zero, C2 is not zero, I don't know. One of them is not zero. Who knows which one? But what I can do, since I don't really know anything about what these vectors are, I'm going to just go ahead and reorder, just rename them so that it's the first one, so that I can assume that that one right there is not 0. And the way I would write that in a proof is I would say, without loss of generality, C1 is not 0. Now because C1 is not 0, I can solve for W1. So I can solve for W1, and that means that W1 is written in terms of V1 and all of the other W's. Okay? Now this is going to use the second fact from the previous slide. This tells me I had a set of W1, W2 up to Wn, and when I remove W1 and put in V1, W1 is in the span. That tells me that this new set with W1 removed and V1 added, this new set continues to span V. Okay, so that is the key fact right there. Okay, so now on to step 2. We still have the same L that we had before, but instead of using G now, I'm going to use the set that we ended the previous step with. So we ended the previous step with G2. So there's G2. It's the same as G, only W1 has been removed and V1 has replaced it. Now we've already handled V1, so I'm going to ignore V1, which means I'm going to look at V2 next. And from the previous step, I know that G2 spans V, just as G did. So that means that I can write V2 as a linear combination of the elements of G2. Okay, so there it is. It's written as a linear combination of all of those elements. Now my goal is to again solve for one of the W's. So I need to argue that one of those constants, the D's, that one of those is not 0. But I have to be a little bit careful. I mean, I know for sure one of them is not 0, but what if it's D1? What if D1 is the only one that's not 0? Okay, well, V2 cannot be written just purely in terms of V1. If all of these other terms right here were 0, then that would tell me that V2 is a constant times V1. But that's impossible because L is linearly independent. So I know that at least one of the D's over there in the purple area, one of those has to also be not 0. Now I don't know which one it is. It could be any one of them. It could be D7, it could be D3, who knows? But what I can do is I can rename and reorder, so I can say, without loss of generality, let's say that D2 is not 0. Okay, so I'm renumbering the W's to make this notationally a little easier. Okay, well, if D2 is not 0, I can solve for W2. And then I would have W2 expressed in terms of, if I solve there, I would have V2 and then minus all this other stuff. So I would have W2 in terms of V1, V2, and W3 up to Wn. So look at this set right here, the set at the end, compared with the original G2. I got this set by removing W2 and replacing it with V2. And W2 is still in the span of it. This is the second fact from the slide 2 before. That tells me that this new set that I got by removing W2 and adding V2, that this set also spans V. So I'll call this set G3. And then I'm going to continue to do this again. I'll do it now for V3, then I'll do it for V4, and so on. Okay, finally let's just talk about what will happen with the very last step. Okay, so we can do it in full generality. So with the very last step, I still have my same L that I had before, and my Gm-1, I would have now have done all of the steps except for the last one. So I would have handled V1, V2, all the way up to Vm-1, and then I just have to figure out how to add Vm to this set. Okay? And again, at the end of each step, I would have shown that G sub whatever spans V. So I can take any particular element, like say V sub m, and write it as a linear combination of those things. So Gm-1 spans V, which means I can write Vm as a linear combination of all of these other things. Okay? Now, is it possible that all of the B's are 0? Is it possible that all of the B's are 0? Well, Vm is not in the span of V1 to Vm-1 because L is linearly independent. So because L is linearly independent, Vm, if all of these were 0, then Vm would be in the span of these, and that would tell me L was not linearly independent. And so that can't happen. At least some of these purple ones have to be non-zero. Because I don't know which one is non-zero, again, I can just rearrange the W's, change the numbering so that I can assume it's B sub m. So we'll say, without loss of generality, B sub m is not zero. Okay, so I can solve for Wm. That means I'll have Wm in terms of all of the V's and then the W's other than Wm. Okay, so Wm will be in the span of this set. And if you look at this set compared to the Gm minus 1, all it is I took Wm and changed it to Vm. Everything else is the same, and Wm is in the span of this new set. So since Gm minus 1 spans, then this new set also spans the whole vector space. Okay, so I'll call this new set G sub m, and this new thing spans the whole vector space. Okay, so now look what I have. I have a whole set here that spans the whole vector space. I'll call that part right there, I don't need to call it L. Those are the elements of L, right? And so what's left over, I'll call that set of those elements, I'll call H. Okay, so L union H altogether has the same size as the original G, and L union H spans the whole vector space. Okay, and that completes the proof of the replacement theorem. Now the proof that I just gave is slightly different than the one in the book. It's basically the same idea, but the one in the book is written in a more technical way. This one that I've done on the slides is pretty informal. Like, this is not what I would want you to hand in for homework. This is much more of just abbreviations and shortcuts and kind of hitting the main ideas, and then the words I'm saying out loud are hopefully making it more formal. I want you to read the handout that I gave you where I wrote down this whole proof that I've done in this video and written it down carefully, and kind of read through it carefully while you're watching the video and identify, which parts of my spoken proof and my shortcuts here and how they're showing up in the proof written like formally and nicely using complete sentences and periods and etc., etc., etc. Okay, so I hope you enjoyed the video, and I'll see you next week.